Everyone is watching NVIDIA, the stock, the GPUs, the keynote slides, the next monster chip. And honestly, that makes sense. NVIDIA is the face of the AI hardware boom. But if you are a cloud company, an AI startup, or a data center operator, the question is not only, can NVIDIA design a faster chip? The real question is much more practical. When can I actually use the compute? That is where the story changes. Because a GPU does not become valuable when it is announced. It becomes valuable when it is manufactured, packaged, tested, shipped, installed, powered, cooled, and running inside a data center. Before that, it is not usable AI capacity, it is a promise. And in the AI boom, a promise is not enough. A startup cannot train a model with a press release. A cloud provider cannot rent out a benchmark. And an enterprise customer does not care how powerful the chip is if the server is not available. That is the hidden business problem behind AI chips. NVIDIA can design the engine, but that engine still has to pass through the factory, the packaging line, the memory supply chain, the server builder, the power grid, and the cooling system before it turns into revenue. So AI chips need more than NVIDIA. They need the industrial machine behind NVIDIA, and that machine is under pressure. The basic contradiction is simple. AI demand moves at software speed. AI chip supply moves at factory speed. A new model can appear almost overnight. A chip factory cannot. A software update can be pushed in minutes. A semiconductor process has to be tested, fixed, repeated, and trusted. That time gap is one of the most important business stories in AI. Look at Blackwell. NVIDIA says its Blackwell architecture contains 208 billion transistors and is manufactured using a custom TSMC4 NP process. That sounds like an engineering headline. But the business meaning is more important. A chip that complex is not just hard to design. It is hard to make again and again. The challenge is not building one amazing chip for a presentation. The challenge is building enough working chips with good enough yield, fast enough for companies spending billions on AI infrastructure. That is where the money is, and that is where the delays begin. Think about the chain. NVIDIA designs the chip. TSMC manufactures the silicon. ASML's EUV tools help print the tiny patterns. Memory suppliers provide HBM. Advanced packaging connects the GPU and memory. Server makers turn accelerators into machines. Data centers turn machines into usable compute. One weak link changes the whole business. If wafers are late, the chip is late. If HBM is short, the accelerator is incomplete. If CoWoS packaging is full, demand cannot become shipments. If testing fails, the product waits. If the data center has no power, the server is just expensive metal. That is the part most people miss. The AI chip shortage is not always about the chip itself. Sometimes the bottleneck is memory, sometimes it is packaging, sometimes it is substrates, sometimes it is server assembly, sometimes it is electricity, sometimes it is cooling. The bottleneck moves, and whoever controls the bottleneck controls the timeline. Start with manufacturing. Advanced AI chips are made in some of the most difficult factories on Earth. These are not normal factories. They are controlled environments where air, chemicals, light, vibration, temperature, and timing all matter. ASML's EUV systems use 13.5 nanometer light to print extremely small chip patterns. That sounds like a science detail. But in business terms, it means one thing. This capacity is very hard to copy. You cannot build it in a warehouse next month. You cannot replace it with cheap machines. And you cannot skip the process just because demand is high. If the tools, engineers, and process knowledge are not there, the chip does not move. Then comes yield. Yield sounds boring until it starts burning money. If too many chips on a wafer fail, every good chip becomes more expensive. If yield improves, the same factory creates more value without changing the design. That is why a foundry is not just a supplier, it is part of the business model. NVIDIA may sell the AI dream, But TSMC helps decide how much of that dream can become real silicon at scale. Then comes memory. This is where ordinary viewers often misunderstand AI hardware. A GPU is not powerful only because it can calculate fast. It also needs data to arrive fast enough. Imagine a factory with the best machines in the world, but trucks bring raw materials too slowly. The machines are expensive, the machines are ready, but the line still waits. That is what happens when compute is faster than memory. AI systems need high bandwidth memory because the chip is constantly moving huge amounts of data. Without enough memory bandwidth, the GPU cannot be fully used. So the real product is not just the GPU die, it is the GPU, the memory, and the connection between them. That brings us to packaging. For years, packaging sounded like the boring end of the semiconductor business. Make the chip, package it, ship it. AI changed that. Now packaging is where performance happens. TSMC describes CoWoS as an essential foundation for high-performance computing and AI products. In plain English, CoWoS helps connect powerful chips with high-bandwidth memory so they can work as one system. That is why packaging capacity can become a strategic bottleneck. A wafer full of powerful dies does not help a cloud company if those dies cannot be turned into finished accelerators. And a finished accelerator does not help if it cannot get into a working server. This is where the AI chip story becomes a delivery story. Cloud companies are not buying chips for decoration. They are buying usable compute. They want racks online. They want training clusters running. They want inference capacity available for customers. They want revenue. So every delay has a business consequence. A memory delay becomes a GPU allocation problem. A packaging delay becomes a shipment problem. A server delay becomes a cloud capacity problem. A power delay becomes a product launch problem. This is how a factory bottleneck becomes a software business problem. Now look at who benefits. The obvious winner is NVIDIA, but the hidden winners are spread across the chain. ASML benefits when advanced chips need advanced lithography. TSMC benefits when leading chip designs need leading-edge manufacturing. Memory makers benefit when AI systems need more HBM. Advanced packaging becomes more valuable when chips get larger, hotter, and more dependent on memory. Server makers, power equipment suppliers, cooling companies, and data center operators all become part of the same value chain. That is the real AI gold rush. Not just models, not just GPUs. The gold rush is moving through the industrial layers underneath AI. And this is why the market can look strange. One company gets the headline, another company owns the bottleneck. The headline company has the brand. The bottleneck company has pricing power. When memory is tight, memory suppliers matter more. When packaging is tight, packaging slots become valuable. When power is tight, data center locations with grid access become valuable. When cooling is difficult, thermal design becomes part of AI economics. That is the difference between a normal tech story and a factory logic story. Technology tells you what is possible. Industry decides what can actually be delivered, and customers pay for delivery. This also explains why governments cannot rebuild chip supply chains quickly. A country can announce a semiconductor plan. A company can announce a new fab. Investors can fund a new factory. But a real semiconductor ecosystem is not built from announcements. It is built from equipment, engineers, materials, clean rooms, chemical control, customer approval, yield learning, packaging capacity, testing, logistics, and years of mistakes. A press release can promise capacity. A factory has to prove it. A supplier can promise quality. A customer has to approve it. A government can fund a plant. But the ecosystem has to learn how to produce the same thing again and again. That is the hard part. So AI chips are not just a Silicon Valley story. They are a Taiwan story, a Netherlands story, a Korea story, a Japan materials story, a data center power story, a cooling story, a logistics story. To the user, AI feels digital. You type a prompt, you get an answer. It feels instant. But behind the screen, AI is one of the most physical businesses in the world. It depends on wafers, optics, gases, chemicals, memory stacks, substrates, copper, water, electricity, transformers, chillers, servers, and people who know how to keep the system running. That is the lesson. AI is sold as intelligence, but it is built as manufacturing. The next AI race will not be decided only by who designs the fastest chip. It will be decided by who can turn chip designs into usable compute again and again at factory scale. Because a chip is not real when it is designed, it is real when the customer can use it. And before that happens, the chip has to survive the industrial machine behind it. That machine is the story. This is factory logic.